We just calculate for the upper part or the half part of that circular loop. The rest of the thing is same, but we just give the notation of the top part. We have length with respect to the circumference of the circle. So we have 2 pi r. Since we are taking half of the circle, we divide it by 2. So 2 cancel. So it is pi r. B into 2 pi r is equal to nu naught by I. So the magnetic field will be nu naught divided by 2 pi r into I. Hello everyone, I am Brinda, Faculty of Physics, welcoming you all to session 1 of chapter 4, Moving Charges and Magnetism. So we all know that till chapter 3 we had studied about current, electricity, generation of electricity, how the charges moves, everything. But there is another component which we have to go beyond and study, that is due to the movement of the charges there is a presence of your magnetic field. So that is what we study over here. So with respect to that, we have certain set of laws. One sort of law is called as Biot-Savart's law. So according to this Biot-Savart's law, we know that the magnetic field is directly proportional to the strength of the current. Again, the magnetic field is directly proportional to the line element through which the current is flowing. The magnetic field is directly proportional to sine of angle theta, that is if this is a conductor, there is a line element over here, call it as dl. The strength of the current, it is directly proportional. Magnetic field is directly proportional to the line element. Magnetic field is directly proportional to the point P, where exactly the magnetic field is absorbed with respect to this conductor, so that we call it as theta, so that can be called as sine theta, and it is inversely proportional to square of the distance between the point we are checking as well as the current element or the line element. Okay, it is square of the distance from where exactly it is connected in this manner, that is from the current element to the point P. You have to square it. So on regulating all these things to a single set, we have dB vector is equal to, that means change in magnetic field is directly proportional to I dl sine theta divided by r square. So dB vector on removing the proportionality constant you have is equal to, and a constant term nu naught by 4 pi I dl sine theta divided by r square. dB vector is equal to IDL sine theta divided by r square. This is the value where the value of this turns out to be into 10 to the power of minus 7. This is the concept of Biot-Savart's law. Suppose if you take it in your vector notation, then dB vector becomes is equal to nu naught by 4 pi I dl r vector divided by r square becomes r cube. That is the vector notation of it. That's all about your Biot-Savart's law. Having the same law as well as the same expression, we are going to derive a important derivation of the expression, which turns out to be expression for a magnetic field at a point on our axis of a circular current carrying loop. So first of all, let us just check. There is a circular current carrying loop whose point of measurement of the magnetic field, that is a certain distance from the center O. So we have a line element, call it as AB is one line element, A dash B dash is another line element of this. We just calculate for the upper part or the half part of that circular loop. The rest of the thing is same, but we just give the notation of the top part. So if we just draw perpendicular to it, that is at 90 degrees, you get this kind of a notation, and joining this point P, you have this notation. The same thing goes out to be in this format. So you have A here. The distance between the element as well as the point is r, and the distance between this, the radius is said to be a. We have to measure the corresponding distance over here. So for which we have, according to your Pythagoras theorem concepts and all, you have that the distance from the center, that is origin to the point P, is known as x. Distance between the line element and the point P is known as a, as well as the radius is known as r. So according to the Pythagoras theorem, we have hypotenuse, square of hypotenuse is equal to sum of square of other two sides. Squaring other two sides, you have this notation. So A is equal to root of r square plus x square is the component what we have. Let us consider this as equation 1. Okay, so that is all about your initial setups. And now let us just check on to the magnetic field by using the Biot-Savart's law. Since we know that Biot-Savart's law equation turns out to be dB is equal to nu naught by 4 pi I dl sine theta. The angle here at this position is said to be 90 degrees to it. That is, we have a 90 degrees to it. That is, whenever the resultant vector acts in this manner, we have two sets of, this is dB sine theta and dB sine theta. Theta turns out to be, the theta angle turns out to be alpha over here, because we are considering alpha notation here, because the resultant vector turns out to be in this manner as well as this manner. When it is resolved, when the resultant vector is resolved into two components, we have this notation dB sine alpha as well as cos alpha. Theta becomes, that is, the angle becomes alpha, because the angle made by this is said to be alpha. This also is said to be alpha. So it makes a 90 degree. The resultant makes a 90 degree over here. So for which we have, since sine theta, that is sine 90 degree is equal to 1, we get it as dB is equal to nu naught by 4 pi I into dl, and sine theta, sine 90 is said to be 1. That is the notation. So we have this notation for your dB. Since we know that there are 2 dBs, so summation of dB, it turns out to be, now the total magnetic field, suppose if we give a total magnetic field with respect to B, then B is equal to summation of dB sine alpha, because we are checking the resultant vector, this component dB sine alpha. So we have how many dB sine alpha? 2 dB sine alpha. So summation of 2 dB sine alpha. We also know that sine alpha is nothing but opposite by hypotenuse. Opposite we have R, hypotenuse we have A. So it turns out to be R by A component. So B is equal to 2 into, what is your dB? dB is nu naught by 4 pi I into sine alpha is said to be R by A, and summation will turn out to be dl for a elemental component. So summation of dl means we have length with respect to the circumference of the circle. So we have 2 pi r. Since we are taking half of the circle, we divide it by 2. So 2 cancel. So it is pi r. So on application here, we have v is equal to 2 nu naught by 4 pi I into r divided by a into pi r. So now it turns out to be b is equal to nu naught by 4 pi 2 times I pi r square divided by a. This is the final set of notation, for which on deriving for a you have into 2i pi r square. A turns out to be, as you have, root of r square plus x square. This is the final answer what you have. Suppose if x is set to be 0, so the distance, if it is set to be 0, x cancels and you have r square, wherein on equating you will get the final set of equation where x will be 0 if the point P lies on the origin. That is one set. So this is an important derivation which you have to know, as well as the expression of it is also very important, as well as the expression for it is also very important. And next we are going on to Ampere's circuital law. Here we have, that is, the line integral for a closed curve which encloses certain set of area is equal to nu naught times the net current which is flowing through that area. Okay, so B vector, this is the magnetic field within that line vector is what we are considering. So this law holds good as a Ampere circuital law. Having this law, there is one derivation, that is, we have to find out magnetic field due to a straight conductor of infinite length. So its length extends, infinite length, carrying current. So magnetic field is always perpendicular to it. somewhere at point P we are checking its magnetic field. So this is the radius, let radius be R, and it is a circle, and the magnetic field always acts tangent to the circle, so it is said to be parallel to the conductor through which the current I is flowing. When this is the condition, having the Ampere circuital law, we have line integral B into dl is equal to nu naught times the net current which is flowing through it. Taking only this term, we have B into dl. So here we have B into integral of dl turns out to be 2 pi r. Integral of B dl turns out to be integral of dl cos theta, cos notation, since theta is equal to, here theta is said to be 0 degrees with respect to current as well as the magnetic field. So cos 0 turns out to be 1. So we have line integral of B dl itself, because the vector notation is being deducted. So B into line integral of dl is nothing but, we have B into, since the circumference we are checking, it is 2 pi r. So line integral of B dl vector is equal to line integral of 2 pi r. Equating this with respect to this, we have B into 2 pi r is equal to nu naught by I. So the magnetic field will be nu naught divided by 2 pi r into I. So this is the final set of notations. B is equal to nu naught I divided by 2 pi r. For this equation, in order to equate it for Ampere circuital law, you can even multiply and divide by 2. So this equation turns out to be 2 nu naught I divided by 4 pi r. So this can be the other set of equation. So that's all about your using Ampere circuital law, you're finding out magnetic field due to a straight conductor of a infinite length. Next we are going on to the force between two parallel conductors which carries current. So we have force between two parallel conductors carrying current. We have two conductors of namely A as well as B, through which the current I1 as well as the current I2 is said to be flowing. So according to Fleming's left hand rule, the force of each of them is acting towards as well as the magnetic field. All three are perpendicular to each other, direction of the current, the force experienced as well as the magnetic field. Force experienced by this current I2 happens over here, so F2, and direction is B2. So we have the force of the I2 current is happening in terms of the conductor through which the current I1 is flowing. Similarly, the components which happens by the current conductor, first current by I1 current happens on F1 as well as B1 happens in the current I2 conductor. So with respect to Ampere circuital rule in case of magnetic field and infinitely length conductor, so the distance of separation is called as D, and the magnetic field B1 due to the current I1 is called as nu naught by 4 pi 2 times I1 divided by D. So this is the set of equation what we have. Force experienced by the B conductor is said to be F1 is equal to I B L sine theta. So we have current I on F1, the current carried is I2. So B1 is 2 I1 divided by D nu naught by 4 pi L into sine theta. Since theta is 90 degrees, sine theta is 1, can consider in this manner. So F1 is equal to 2 I1 I2 divided by D, and nu naught by 4 pi is added over here, and the length L is added over here. So this is the final set of equation. Similarly, applying to another conductor, it happens in the same manner, and we get F2 equation said to be nu naught by 4 pi 2 I1 I2 divided by T into L. So both equations holds good for each other, because on each one of the conductors the same concept of forces been acting. So this equation is nothing but the force which is acting between two parallel conductors which carries a current. On this we get a conclusion as Force is directly proportional to the length as well as the current, and it is inversely proportional to the distance. So this is the final conclusion of it. So we have discussed about the magnetic moving charges and magnetism concept, out of which we have picked up some important concepts and concept classes being done. Let us all meet in our next upcoming sessions. Until then, have a good day. Thank you.